Iceberg Robotics is proud to submit our system acceptance review video for consideration by the 2022 University Rover Challenge Judges Panel. Entering our 6th year with support from UAA and many professional organizations, our team chose to iterate upon and optimize last year's design. We proudly present Iceberg 4.
Iceberg Robotics is divided into teams dedicated to each rover subsystem: mechanical, electrical, software, science, and project management. We updated our Gantt chart and task list based on new challenge requirements and available resources. By utilizing FEA on mechanical structures, 3D printing, industrial machining equipment, and software development frameworks, we rapidly prototype and optimize new designs and reformulate old ones.
Iceberg 4's chassis was designed around the extreme retrieval task and remains largely unchanged from last year. It consists of a main structural member cut from 2-inch square tubing that runs the length of the chassis and 2 custom C-channel beams that contain suspension elements.
The rover runs on a 720 watt-hour lithium-ion battery pack, providing ample power for each competition task. 5 cameras face in various directions to give the driver sufficient visibility at all times. These provide multiple close-ups of the end effector and wide-angle views of the arm and rover. The rover uses a set of 900 MHz ubiquity radios to carry multiple video streams as well as rover commands, allowing maximum propagation across terrain. A pair of 5 dpi dipole antennas are mounted high on the rover, while the base station uses a 120-degree directional antenna with a 13 decibel gain.
The base station runs a custom graphical application built with WX Python for viewing rover camera streams and monitoring and controlling the rover. It utilizes a navigation system to display the position of the rover in real time from transmitted GPS coordinates, and a configurable control system, enabling operation of the rover with a pair of gamepad controllers.
For the autonomous traversal mission, the rover uses an onboard GPS and accelerometer magnetometer to precisely determine its position and orientation. The OpenCV and TensorFlow Python libraries analyze image and depth data from a stereoscopic camera to detect obstacles and hazardous terrain and identify competition markers. Our pathfinding system uses a record of data from encountered obstacles as well as classification machine learning algorithms run on an NVIDIA RTX 1060 GPU to calculate the most direct path to waypoint coordinates. We use these data and models to train a convolutional neural network to aid the rover to better identify key competition objects and avert potential hazards.
The arm design drew inspiration from a number of industrial sources. The shoulder is powered by a 200-pound linear actuator, minimizing any moment forces in the upper arm. The elbow uses a 3-to-1 worm gear transmission that provides smooth, predictable motion and over 100 pound-feet of available torque. This design allows the forearm to be offset from the upper arm to gain 360 degrees of freedom. We elected to use a worm gear on the wrist.
The end effector utilizes a gripper and a screwdriver system to accomplish the extreme retrieval and equipment servicing task. 3 DC motor and a linear actuator provides a clamping force of 13 pound-feet and a range of 2.5 inches with precision control of 9/100th of an inch. Paired with the robotic arm, the end effector has a 5-axis range of motion. The main task is controlled via the worm drive gearbox, minimizing power draw. A 3D printed enclosed prevents dust from entering the gearbox and belt drive system.
The science plan encompasses a combined approach that includes visual observations, an array of sensors, and wet lab chemistry to identify signs of life. A camera scans the area for the presence of animals, metabolic wastes, tracks, microbial mats, iron staining on surfaces due to microbial metabolic activities, and fossils. Soil and mineral samples are analyzed with a variety of sensors and a computer program that uses Arduino and spectroscopy. The samples are then added to a luminol mixture to observe luminescence levels to determine the presence of oxidizers, including hemoglobin, proteins, urine, feces, copper, or iron. The commercial off-the-shelf Denisi Power Soil Kit consists of 6 different solutions that purify the soil samples. Then it is tested using a NanoDrop 1000 spectrophotometer to deliver a reading of DNA concentration, DNA purity, and nucleic acid purity. Finally, the samples are introduced to hydrochloric acid to test for limestone, which could indicate liquid water and potentially life, in the planet's past.
This concludes our 2022 SAR submittal. We appreciate your consideration and look forward to seeing you at the Mars Desert Research Station this summer.